Today I have made a Slayer exciter circuit to drive my Tesla coil. This is basically the easiest Tesla coil driver you can make. I have modified it a bit to make it work a bit better. This is the circuit. I power it with 12 volts from my computer power supply. We have a fan for cooling since it can get hot. Then we have a couple of components like this capacitor, which acts like a Class C amplifier. So basically it stores charge and then releases it. And it also acts like a filter so that it's better for the power supply. The reason I have some LEDs and diodes here is because I'm using a 45 volt MOSFET instead of a 600 volt MOSFET. So I need to protect it somehow. And these LEDs limit the voltage. The Slayer exciter works basically by turning on and off current in the primary based on the voltage in the secondary. So here it's connected to the base of the secondary and it goes to the gate of the MOSFET. And it turns the MOSFET on and off, which switches on and off power to the primary. Now that we have seen the Slayer exciter circuit, we can start measuring some stuff. In green, I have the voltage in my device. So I'm measuring with the series between the ground and device. Like this, I can sort of calculate how much voltage is in the top load of the Tesla coil. In blue, I have current. So I can measure how much current is consuming the Slayer exciter, so that I can calculate the watts knowing that my power supply is at 12 volts. Now we can turn on the Tesla coil. We can see that we have some current draw between the 1.5 amps and the 2.5 amps, about 2 amps on average. The voltage jumps up to 20 volts. If we zoom in, we can see that we have these things which are supposed to be sine waves. If I had the extra high speed instead of only the high speed, we would see better. And here we can see that we have about 200 kilohertz. Again, it's not a perfect sine wave, so depending on where I measure, it can seem a bit different since we don't really see the peak. We can also see that the current is going up and down at the same frequency, at 200 kilohertz, and we can see that it's almost at the peak. It's probably at the bottom. It starts drawing current, but my components aren't super fast, so it's a bit of phase shift probably. So here we have it. This Tesla coil can transmit power into my device. It's not very efficient since you're at 12 volts. 2 amps would be 24 watts, which is more power than my device is getting. And this is because the Slayer exciter is inefficient, the Tesla coil is inefficient, and the Tesla coil is transmitting to everything around it, not only the device. So even more inefficiencies there. But we can still get some voltage, and if I get a fluorescent tube or CFL and put it in here, it can turn on. Though the range is quite small since the amount of power transmitted goes down by the square of the distance. So twice the distance, a fourth the power. Or at least this would be how it's optimally, but the electric field is bent towards grounded objects, like the power supply, the ground, probably the wall, and so on. In the future, maybe even today, I don't know, I would like to make a better driver, like using a half bridge, since I would like higher power. It's basically can't do arcs. If I have a grounded wire, it will make like a 3-4 millimeter arc to the grounded wire from the top load. However, I know it can do more, and I can't do any like corona discharge or brush discharge. So I want to make a more powerful one. Also because surprisingly, the power draw doesn't go up that much with more if I absorb power. For example, if I put a fluorescent tube nearby, the power draw doesn't go up that much. I think this is simply because I'm bending the electric field to the fluorescent tube instead of like sucking more power, though I'm not sure. Anyways, I don't have much else to say, so bye.